So you've probably heard a lot about flash flooding in the news lately. And if you found your way to this video because you're wondering how it's possible for the atmosphere to dump so much water at once, well, the best way to think about this is, believe it or not, freight trains. Yes, freight trains. Based on conventional knowledge, you might think of flash flooding as something that happens when it rains a lot in a short period of time. The heavier the rain, the greater the flood risk. But if you think about all of the times you've experienced really heavy rain, why did most of those events result in nothing but some ponding on the streets? But then at other times it causes an epic disaster like what we saw in the Texas Hill Country recently. So then you might think, maybe it's not just about how heavy it rains, but how long that heavy rain lasts. If you thought that, you are correct. But hold on, there's a catch. If you watched last week's video about convective versus stratiform rain, I mentioned how warm air rises in an updraft in a convective thunderstorm, and the moisture in the air cools and condenses to form a rain in the downdraft. Well, if left to its own devices, the thunderstorm will eventually build up so much cold air on its backside that it ends up choking itself off from the supply of warm, moist air that sustains it. So this is why most summer thunderstorms don't last for more than an hour. So how can you get heavy rain to last for a long enough time to cause flash flooding? The secret sauce is a special combination of wind speeds and directions in the atmosphere surrounding the single convective thunderstorm, so that new storms that form next to the original storm end up moving over where the original storm was, effectively extending the life of the heavy rain experienced in one single spot. Let's break it down. Let's say you have a single thunderstorm, and based on the average of the surrounding winds through the vertical layer of the atmosphere that contains this storm, it moves to the northeast. This is what we would call the storm cell motion. The term storm cell is just what meteorologists call a single convective thunderstorm. But due to a combination of factors, specifically the orientation of the supply of warm, moist air coming out of the south from the Gulf, new storm cells usually initiate to the south of the original storm cell. This effectively means that the storms propagate to the south, even though the individual storm cells move to the northeast following the average surrounding winds. This results in the entire system of storm cells appearing to move toward the southeast. So if we zoomed out and looked at the big picture, we see that as each progressive storm cell forms, moves toward the northeast, leaving behind the cold pull of air on its backside, that cold pull of air, right where it meets the warmest of the air on the south side, forces the warm air to rise, which forms a new cell, which then also moves toward the northeast. This propagation of new storms toward the south, while individual storm cells move toward the northeast, causes the entire system of storms to move steadily toward the southeast. This is the classic case of a squall line moving through an area. If you look at a radar animation of this process unfolding, it almost looks like an optical illusion. Individual storm cells form and move toward the northeast, but the entire system of storms actually moves toward the southeast. This organization of thunderstorms is pretty typical. But then there's a special case. When the wind directions across the depth of the layer of the atmosphere that the storm is oriented in just the right way, the propagation vector can point in the exact opposite direction of the storm cell motion vector. In other words, new storm cells form directly upwind of the previous storm cell, which means as it forms and moves toward the northeast, it ends up raining on the same location over and over again. Zooming out, we see the same elements as in the more typical case of squall line motion, with the convergence of the southernmost part of the cold pool and warm air initiating a new storm cell. But because the storm cell motions are all toward the northeast, the system itself has no motion and effectively remains stationary. You just have one storm cell after another, moving over the same location for hours on end. This is what meteorologists call training thunderstorms. Just like a freight train with multiple cars, each new storm cell follows the previous like on a track. So what would have only been a few minutes of heavy rain potentially extends to many hours. The potential for training thunderstorms is one of the primary ingredients that meteorologists keep an eye on when determining the risk for flash flooding. That said, many other factors also come into play to determine whether a flash flood actually occurs. How much moisture is available to feed the storms? Where is the rain falling in relation to the topography? Like, is it over a flat area where the water can easily spread out? Or in the headwaters of a river valley where the water is funneled down the river and has nowhere to go but up? Is the soil already saturated and wet from past storms on past days? Or is the soil bone dry thanks to a drought? Both of which would cause rapid runoff of water since the soil can't quickly hold on to it. These and many other factors must be considered for proper flash flood forecasting, and successfully predicting the weather is just one piece of the big puzzle. We will explore more of these factors in future videos, so be sure to hit subscribe as I take you on a journey of making sense of the untamed skies.